Okay, this is Friday 4/21, and we are starting the notes on sequences and series, and we have a few people absent, so I made an executive decision to record this lesson, and I gave everybody a homework sheet. So if I knew you were gone, I think I have given you a homework sheet. If I didn't know you were gone, I have not given you a homework sheet. And we're working on 9-1 sequences and series today. And so we're going to use sequential notation to write the terms of sequences. We'll use factorial notation. Just give me a head nod for those of you in here. Do we have no factorials? Yes. Yeah, okay, or we haven't maybe used them for a long time. And then we're going to use summation notation. If you don't or do remember that, that's this deal. Does that seem familiar to you? You maybe haven't used that for a long time either. And we'll find the sum of some series, just adding up all the terms. So a sequence has comments between it, and it's just a list of things. Series is the sum, they have plus signs between them. And then, of course, always use sequences and series to model and solve real-life problems. So we start with sequences in this section. And, you know, this slide just says these are a collection of things, and they're in some kind of ordered sequence, and so that's why they're called sequences. Mathematically, you can think of a sequence as a set, as a function whose domain is the set of positive integers. So what that really means, if we have this simple sequence that's 1, 3, 5, 7, this is the y values of the function, and the x values are not listed, but they are the term number. So 1 is the first term, 3 is the second term, 5 is the third term, 7 is the fourth term. So the domain is hidden from us. The domain is the counting numbers 1, 2, 3, 4. On occasion, the domain starts at 0. Yep.
So it says here, like the domain is positive.
Right. So I know they could have said whole numbers instead of positive integers, but it is always, so you're counting how many terms. So the first term, second, third, fourth, and that's all it is. And so rather than use function notation, sequences are usually written using a subscripting notation. So here's the definition of a sequence. The definition of a sequence is an infinite sequence, so that goes on forever, is a function whose domain is the set of positive integers, and the function values a sub 1, a sub 2, a sub 3, a sub 4, dot, 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 a sub n, dot, 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 are terms of the sequence. When the domain of the function consists of the first n positive integers only, then it's a finite sequence. So, you know, if we only go from a sub 1 to a sub 12, then it's a finite sequence. So when we're looking at this, the hidden domain is like that subscripted number, correct? And on occasion, we start with a sub 0 instead of a sub 1. So sometimes that messes people up a little bit. You just have to be careful when that happens. When it tells you the a sub 0 term, then you just have to be aware of that. And so that puts off the numbering of those as you go. The reason a sub 0 is a good thing to know is when it's a linear listing or exponential, then that 0 term is actually where the y axis would be, or the y-intercept. Okay, so here's problem number 1a. The first 4 terms of the sequence given by So we're going to figure that out. What's our first one? Maybe we'll do it together. Um, and so we can either use the n value or we can use the subscripted, a sub n or a sub n minus 1 for a previous term. So this one, the first four terms, we just put in a1, n equals 1, 2, 3, and 4. And we use n equals 1, 2, 3, and 4, and we just find the terms. So a sub 1 is 3 times 1 minus 2, which is 1. A sub 2 is 3 times 2 minus 2, which is 4. A sub 3 is 3 times 3 minus 2, which is 7. A sub 4 is 3 times 4 minus 2, which is 10. And if I list these out, 1, 4, 7, and 10, and kind of go dot, dot, dot. What do you notice when you just see the list of numbers? We're adding 3, and later on we'll know that's arithmetic sequence, or in the past you've maybe known that also. And our first term is 1. So we could, once we kind of know this and have kind of listed them out, we could just add 3. Notice also in this a sub n form right here that 3 would be the slope if that's considered a linear situation as we look at that. So just kind of something to think about. Also, just for subscripting purposes, n is very common. I, j, k, and n are our common subscripts. Just like when we're doing coordinates, we use x and y, and when we're doing triangles, we often use a, b, c, and things like that. So here is, oh, just a second. Oh, I thought I cleaned these up. Okay. Here's our next one, and this is 1b. A sub n is 3 plus parentheses negative 1 to the n. And you're going to find the first four terms of that. So a sub 1, a sub 2, a sub 3, a sub 4. I'll give you a moment to figure those out. Are you noticing anything about this one as you figure them out? They're not all the same. What's happening? So I'll start writing them in here. So you should notice that this one's going to oscillate between 2 and 4, right? And like on the last one, where's that first sequence headed? To what? When we added 3, that's going to infinity. Is this going to infinity? No, actually, it doesn't go to anything, right? Because it oscillates between 2 and 4. So it actually doesn't have a limit if we go out to infinity. And so this is an alternating one. Kind of think about that -1 and the impact that that's having. So then here's our next one. Write the first four terms of that sequence and see what you get. I'll do it in the same at the same time, but I'll write in white. Did you get the first term yet? What is it? Negative 1/3 is the first term. Um, and I couldn't write everything here as I went. And did you get the second term yet? Is positive 1/5 for that one. And did you get the third one? Negative 1/7. And the fourth term? Positive 1/9. So I want to just notice what makes it oscillate between negative, positive, negative, positive. Negative 1 to the n. So suppose I wanted this one to be positive and then negative, positive, negative. How could I change that negative 1 to the n? No, if the n was negative, that would just mean 1 over. So how could I change that negative 1 to the n to make instead of the first third, the odd ones, I could, if I wanted to still start with 1. That is correct. I could start with 0 and have it work. But if I wanted to start with 1, n would have to be something different. What could it be? Minus 1 or plus 1. If we subtract, oh wait, let's think about whether we should subtract 1 or add 1. What if it's n minus 1? So what's 0 minus, or 1 minus 1 would be 0. What's negative 1 to the 0? It's positive 1. So that would work, right? And what if I wrote it as n plus 1? Well, what's 1 plus 1? 2, and would that still make it positive, that first one? Yes. So that's kind of something to think about as we go, because our job is going to be to make up the rules as we go. So you have to know if you see a sequence and it alternates positive and negative signs, you have to know that you're going to use negative 1 to either the n or the n plus 1 or the n minus 1 or something like that. So 1/3, 1/5, negative 1/7, and 1/9, and if it goes on forever. So here's another sequence. Suppose I tell you I have 1/2, 1/4, and 1/8. I want you to think about this. Do you know without a doubt what the next term is? Let me ask a previous question. Can you get a next term using some kind of rule? Could you get a next term? What would it be? What would your next term be? Okay. It could be 1 over 16, right? Or, well, adding 2 and then adding 4, and then could you add 6 would be, I don't know. Okay, so let me go back to the question I asked. Um, Let me go back to the question. If I gave you that, do you know without a doubt what the next term is? Exactly. Watch. Here are two sequences that turn out with that same beginning pattern. So look, it could be 1/2, 1/4, 1/8, 1/16, which is 1 over 2 to the n, which you're familiar with. Look, it could be 1/2, 1/4, 1/8, 1/15, and it's using this rule. And when you put in n equals 1, 2, 3, and 4, that's the values that you got. So I'm going to tell you that in your future, are you ready? In your future, you've got to come up with a bunch of these sequences and things like that. So I'm suggesting that you make a table of values right now to help you decide on sequences and series, because eventually we're going to narrow in on arithmetic and geometric sequences and series, but right now it could be any sequence or series. So I want you to make a table of values that has 1 through 5 is n, and then I'd like you to make these are kind of common things, and I've since then added two things, but they're not on my main slide. This and this. So take a minute, write that table of values. And we're going to use that table of values to compare to some first terms in a sequence and kind of come up with hopefully what we think are going to be some values. I'll show it and then I'll pause it for a moment or two. So I'll pause this and you can write some of that down and then I'll start back. Okay, so, and there's the last two rows if you didn't get those, and I made a little handout of that for myself so that I can see it on as we go. So I'm calling these reminders of patterns because remember what you're going to see in a moment is just a list of numbers, and you want to draw from maybe one of these. These are common patterns of numbers, and so the 1 through 5 that's written up here, that's like the term number. So this is a sub 1, you know, a sub 2. That's what these 1s and 2s are standing for, that hidden domain. And, you know, are my numbers increasing by, you know, the same amount? And maybe they're based. If I notice that I'm adding 4 every time, there's probably a dynamic of 4n in there, but maybe it's just not 4, 8, 12, 16, 20. Maybe it's 5, 9, 13. What would the next one be? 17. What's the next one? 21. So are these still adding 4? Yes. So we're using this pattern of 4n, but it would be 4n plus 1 or n 1 plus 4n or something like that. So you want to look at these kind of basic patterns and then see what's happening. And so if it were 5, negative 9, 13, negative 17, 21, where it's alternating negatives, then instead of being 4n plus 1, it's going to be 4n plus 1 times this negative 1. Oh, I didn't leave myself enough room. Raised to the n plus 1 to make those alternating signs. Okay, so this is just a little table of numbers, patterns, to kind of just help you as you go through and are trying to figure things out. So that's why, in a way, I think this first section is harder than the next two sections, because the next two sections we're just focusing on arithmetic sequences and series and geometric sequences and series. So you come up with a rule for the nth term. Here they are. The first one is at 1, 3, 5, and 7. So think about your hidden domain. This one's going to be pretty easy. Your hidden domain is the 1, 2, 3, and 4. And let me I'll just slide that a little bit that way. And so I have to think about if I start with 3 here, how am I going to get 5? Or if I kind of have whatever the number is there, how am I going to get to the next one? So how am I going to get 1 when I put in 1? So I can't just say it's n plus 2. I have to be able to say, what am I going to do to get that value? Well, they go up by 2, right? So what in the pattern goes up by 2 in any of these? Not 2 to the n. These don't always go up by 2. 2n. So let's just kind of build it. So we're going to build it. Yep, 2n would be 2, 4, 6, 8. And now what's the relationship there? 2n minus 1. And then that would give us the 1, 3, 5, and 7. So our rule here is a sub n equals 2n minus 1. Okay, here's our next one. Are you ready for the next one? You want to try it? I just want to know. What are you noticing about it right away? It alternates, so we're going to use that as a dynamic, right? That's going to be happening. Um, I like to just ignore that for now because I just know I'm going to multiply by that and it'll give me my negatives. So I'm going to do an alternate pattern of 2, 5, 10, and 17. So we know that our n is 1, 2, 3, and 4 for that. So are these going up by a constant? This is add 3, this is add 5, this is add 7. So is it any of these 2n, 3n, 4n, 5n's? No, because they all go up by the same amount. So test for yourself. Do you think it's n squared that it's based on? Do you think it's 2 to the n? And I only wrote 2 to the n, but it could be 3 to the n, 4 to the n, 5 to the n. You like n squared? Okay, so let's think about n squared, and maybe let me put my n list in there first. So n equals 1, 2, 3, and 4. N squared, what is n squared? What is n squared?
1, 4, 9, 16.
Okay, and what have we done to those? So n squared plus 1 is 2, 5, 10, 17. What do we have to do to that rule? We have to oscillate the negatives. Ooh, I like that. And so to oscillate the negatives, keep in mind that has to be in parentheses then. And which one? We want positive first. So it's negative 1 to the n plus 1 times n squared plus 1. And do you agree that's kind of a complicated looking rule? But if we have kind of a little pattern chart to get us started, it becomes a little bit easier. So a sub n is negative 1 to the n plus 1 times n squared plus 1. And by the way, I put these in there. When we get to the next section, these ones and all, these ones that go up by a constant amount, those are going to turn out to be in section 9.2, the arithmetic sequences. And I only put 2 to the n, but we could have had 3 to the n and 4 to the n and all that. And those are going to be geometric where there's a constant multiplier. So this one is neither of those. And n squared is a common kind of beginning pattern to kind of look at. So now I'm going to tell you that some sequences are defined recursively. So in those last ones, do you agree that once we figured out n, if I wanted like the 854th term, I would just put in 854 for n and follow the equation and get it, right? So recursively means that it's defined based on the previous term to get the next term. And so then to get the 854th or whatever term, I'd have to find all those terms to get there. So some sequences are defined recursively, and to define something recursively, you need to be given one or more of the first few terms, or one term and a rule of how they are defined using the previous terms. So if you're at the first, second, third, and fourth term, what's the next term? The fifth term. So if you're at the fifth term, what was the previous term? The fourth term. So if you're at the nth term, what was the previous term? The n minus 1 term. So that's how we'll be defining things. And sometimes we'll define them in terms of the n minus 1, the n minus 2 terms, where we have to look back several terms. So here's our first recursive sequence. Number 4, write the first 5 terms of the sequence defined recursively as, and I'm just going to rewrite it. A sub 1 is 3, and A sub k is 2 times A sub k minus 1, that's a whole subscripted, plus 1. And then they're just telling us that k has to be greater than or equal to 2. So we want the first 5 terms. We have, oh, do you want me to wait a moment? So here A sub 1 is given for us, and so then we just follow this rule, and I'll write these under A sub k. So A sub 2 means k is 2, so it's 2 times A sub 2 minus 1 plus 1. For this first one, I'll kind of write a little bit more out, then I'll quit that. So it's 2 times A sub 1 plus 1. And so A sub 1 is 3, so it's 2 times this 3 plus 1. And so that was a long and involved 6 plus 1, so 7. So now I'm just going to shorten that up. A sub 3 is going to be 2 times the previous term, which is 7, and then add 1. So that's 15. A sub 4 is 2 times the previous term, which is now 15, plus 1, which is 31. And A sub 5 is 2 times the previous term, which is 2 times 31, plus 1, which is what? Oh, no, it isn't. 63. 62 plus 1 is 63. So for this one, the first 5 terms are 3, 7, 15, 31, and 63. The next sequence is defined recursively, and it's the Fibonacci sequence. You just have to tell me, do you think you've had the Fibonacci sequence before? Okay, and the Fibonacci sequence is the most frequently occurring sequence in nature. And right, yes, and it's the basis of all of that. So here it is defined sequentially, and you're going to find, oh, let me find that slide. There it is. This is number 5. I'm going to pause a moment and give you, the people in the room, time to figure out the first 6 terms. I want you to do it by yourself. If you are nervous about getting them right, I can give you a blank sheet of paper to write them on. Or if you were feeling more confident, you can write right on your paper. It's up to you. And you are noticing that it's the A sub 0 term that it starts with. So I'll pause the recording. When I come back on, I'll just go over this problem. Okay, so we've had a little time to do this. Does anybody want to tell me what they think it is? Oh, okay, wait. Oh, the first two are 1, 1.
Okay, 1, 1, 2, 3, 5.
Yes. Okay, so let me just kind of, oh, is that the phone again? Darn. Okay, so now I think I'm back on track. Okay, so let me just go through this. We had another little interruption. So a sub 0, and by the way, notice on this one that's a sub 0 that equals 1. So it is starting with a 0 term. So the sixth term is a sub 5, right? So if you are asked to write those out like on a test or something, you know, and it says the first 6 terms and it starts with a sub 0, you just go to a sub 5. So a sub 0 is defined as 1. A sub 1 is also defined as 1. Then a sub 2 is equal to, well, if k is 2, then this is 2 minus 2. So that's a sub 0, which is just going to be a sub 0, I'll write that. And then this one is a sub 2 minus 1, which is plus a sub 1. So 1 plus 1, which is 2. Then it's really just recursively adding the 2 previous terms. So a sub 3 is 1 plus 2, which is 3. A sub 4 is 2 plus 3, which is 5. A sub 5 is 3 plus 5, which is 8. So the first 6 terms are 1, 1, 2, 3, 5, and 8. Got it? Okay. So now we're going to look at factorial notation. Wow, I couldn't even say that. Factorial notation. And you've encountered those before. So factorial notation that is defined as, if n is a positive integer, then n factorial is defined as n exclamation point, which is 1 times 2 times 3 times 4, dot, 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 times n minus 1 times n. And as a special case, 0 factorial is defined as 1. So you just want to remember that as you go. And on your little calculators, does it have a factorial key? Factorial key? I'm guessing it does somewhere. Sometimes it's a little hidden. Um, in the graphing calculators, it's under math. I don't know where it would be. So that could be a little investigative thing. Maybe somebody can tell me on Monday where that is. And so I'll just write a couple of them out. 0 factorial is 1. 1 factorial is also 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. What is 10 factorial? And maybe use that calculator and do it as just 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Oh, I didn't write 9. Times 8 times 9 times 10. 3628800. So notice, you know, from 2 factorial being 2 and 3 factorial being 6, just a 10 factorial is 3,628,800. And so factorials become very big very fast. And at some point, our calculator can't always handle factorials. And you do have to be careful. Here's my question. If I have 2n factorial and I have 2n in parentheses factorial, are those the same thing or different? These are different. Those are different. So just a little reminder of that. And I have on the next slide just something about that, that that makes sure, oh, maybe it's not the next slide, it's the next couple slides, that 2n factorial is 2 times n factorial, and 2n in parentheses factorial means we go to from 1 to 2n. Oh, yes, okay, so wait, we're going to tell everybody where the factorial key is. If you push PRB on the little calculators, and then it's the third one down. Third one down is the factorial key. Factorial key. Okay, good. So now you know that. And it is, probability is where we use factorials quite a bit. So we're good to go there. Okay, so I will put up problem number 6, and this is the one we'll work on Monday. Have a good weekend. Oh, Riley Lubin wanted me to tell everyone hello.